So ultimately, these next two are about counting, how to count something based on whether there's an order or not. So if you think of a lot of things in your life, you arrange something on a bookshelf, you're hanging up pictures on a wall. There's a certain number of ways you can do those things, and the order is going to be important because if I put this picture up first or this book first, it's different as if I put it at the end. So there's a structure to that. But in other ways, you might be choosing something. So maybe you decide you're going to choose some fish and you go to a store and you buy some fish for your fish tank. The order you pick the fish doesn't matter because you're still getting the fish at the end of the day. But there's still a number of combinations that you can possibly pick from those that are available. So these two sections kind of go through the distinctions. How do you count the number of ways when the order matters versus how many ways when the order does not? So this first section, permutations, is going to be when that order is important. So the first thing we're going to do is recall that counting principle. So recall if there are m ways a first experiment can be performed, and n ways a second experiment can be performed, then there are m times n ways the two experiments can be performed in that order. Okay. And the same holds if I have 3 experiments, you multiply the number of ways. 4 experiments, multiply the number of ways. So let's do a quick example, just kind of refreshing ourselves with this principle. Maybe you decide to enroll in 4 classes. You're going to enroll in a sociology course, a chemistry, an economics, and humanities course. Sorry, my puppy's whining on the floor. So you're going to pick one of each of these classes, and let's pretend it's virtual, so this way nothing is going to overlap. So in total, there are 7 sociology, 4 chemistry, 3 economics, and 4 humanities. Classes that fit your schedule. Okay. So you have a lot of possibilities. I am definitely not going to sit here and try to draw a tree with this. I just want to know how many different ways can you select your classes? So let's take a look. I've got 4 different classes I'm picking. So you're going to see me draw these kind of lines over and over. Each of these is going to represent one of those subjects. So when we go to pick our sociology, we have 7 possibilities. For chemistry, there are 4. For economics, there are 3. And for humanities, there's 4. Okay. So these are the number of ways for each event. What we do is just multiply them together. So the number of ways is 7 times 4 times 3 times 4, which is 336. So ultimately, there are 336 ways you can pick your schedule. So a ton of possibilities that I definitely don't want to go through and try to list them all out. Right? All right. Let's try some more of these before we get into what a permutation actually is. Let's work with some passwords. Maybe you have a very specific site. You might notice like a lot of them require you have at least this many letters. You have to have a special character. You have to have a special number. Some of them don't let you do that. So maybe we're at a site and we're told a password must consist of 2 lowercase letters followed by 4 digits. We want to determine the number of passwords if first repetition is allowed. Okay. And so that means I can repeat a letter or I can repeat one of the numbers. So ultimately, you need to know how many possibilities there are. So in total, there are 26 letters. And then the digits is a little bit hard. You actually have 10 digits. So you have 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So that 0 kind of throws you off a little bit because it adds an extra digit. Okay. So ultimately, the password is going to look like the following. So I've got 2 letters at the front. So a letter, and then 4 digits at the end. So this is a digit, a digit, a digit, and a digit, okay? So I can repeat letters. So I have 26 options for this first letter, 26 options for the second. So each letter has 26 choices. For the digits, I can use the same number over and over. So I have 10 options in each slot. So each digit has 10 choices. So when I want all possible passwords, I just multiply these numbers together. So in total, there are 26 times 26 times 10 times 10 times 10 times 10, which if you multiply out, there are 6,760,000 possible passwords. So a lot of possibilities. And this is a pretty restrictive password input. So you add more letters and you don't add a specific order, there's a lot of possible passwords, which is why you don't want to choose common ones. Okay. If I add another criteria now that I can't repeat anything, we'll see how that affects it. So repetition is not allowed now. Then we don't have as many because I'm losing some of my options. So I still have the same setup of a letter and a letter, followed by 4 digits. When I go to select that first letter, I still have 26, but now I can't repeat it. So whatever letter I've picked is out of my pool. I have 25 letters left to choose from. So here there's 1 less letter. And likewise, the same thing happens for the digits. You start out with 10. Maybe I put an 8 there. Well, now that's out of the pool. So I have 9 left to choose from. Then I have 8. Then I have 7. So here, each time, there's 1 less letter or digit. Okay. And so in total, we just multiply these again. So there are 26 times 25 times 10 times 9 times 8 times 7. And now you don't have nearly as many possible passwords. It cuts it down really in half to 3,276,000 possible passwords. So a lot less. Okay. So in both of these situations, really, we already knew the order of what had to happen, but a lot of times you don't know that. You just have a collection of objects and you want to arrange them. And so this is what that permutation is going to do. It's going to be the ways we can order these things. So in these situations, the order of letters and numbers was already given to us. But we could figure out how many ways we can arrange the letters and digits. And this is exactly what a permutation is. So a permutation is any ordered arrangement of a given set of objects. Okay. And so ultimately, we're going to figure out how to come up with that. So I don't have to sit here and try to draw every possibility or try to go through and calculate things on my own. We're going to end up with a nice formula, but we want to figure out how to get there. So I'm going to start with an example that we can actually do. So we're going to determine the number of ways to arrange the following pictures. And so go ahead, try to pick things that I can draw fairly easily. Let's draw a smiley face because that's not too hard. Make it a little tiny. So we've got our lovely little smiley. I'm going to give him a little bit better of a mouth. There we go. And then let's do a cloud because that's also relatively easy. And then I need one more picture. Let's just draw, let's draw a triangle. Let's be even more fun. Let's make it fun. Let's make it the Deathly Hollow symbol, because why not? If I want to get a straight line in here, there we go. 3 not so bad pictures to draw. Okay. Well, really, this is one way we can arrange those 3. Okay. The second possibility is I can still keep my smiley face right up front, but then I can switch the order of these 2. So I can put my Deathly Hollow symbol followed by my cloud. Third thing I can do is, well, I've exhausted my possibility of my smiley going first. Let's put the cloud first. Okay. And then we could put our smiley first before the Deathly Hallows. And likewise, I can flip the order of those. So cloud goes first, then Deathly Hallows, then we've got smiley. And then really one more possibility for what goes up front, we can put that Deathly Hallows symbol. And then we can put the cloud second, the sun third, or smiley third, and flip those. So Deathly Hallows, smiley, cloud. Okay. And now I've exhausted every possibility. So in total, there are 6 ways to arrange the 3 pictures. And I'm going to shrink this a little bit so I have enough room to write. So realistically, it didn't matter what pictures I put there. If I change these to 3 objects, 3 books, 3 mugs, whatever it is, this is the only possible combinations of what I could go through to arrange those. So there are 6 ways to arrange 3 objects in general. So as kind of a note, let's kind of relate it to the way we were going back through this. Okay. I have 3 pictures. So I have 1, 2, 3 things that I'm arranging. So this is my first picture, my second, and my third. Kind of doing exactly the same thing, I have 3 possibilities for this first slot. Once I've set that picture down, I have 2 possibilities for the second. Once that picture's been put down, I have a single one left here. And if we multiply these, that's 3 times 2 times 1, which is exactly the 6 ways to arrange 3 objects. And this is going to happen a lot. If I ask you for 8 objects, you have 8 for the first position, 7 for the second, and you keep losing one until you get down to 1. So the number of permutations of n distinct items is n factorial, which is denoted as n with an exclamation point. Which where this means n factorial is you start with exactly that number, you multiply it by the next number down, multiply it by the next number down, and you keep going until you multiply by 1. So 3 factorial is 3 times 2 times 1. 4 factorial would be 4 times 3 times 2 times 1. So if I'm arranging 7 pictures, it's 7 times 6 times 5 times 4 times 3 times 2 times 1. So that's going to be 7 factorial. So just as some examples with factorials, 3 factorial is you start at 3 and you keep decreasing by the integer till you get down to 1. So 3 factorial is 6. 4 factorial is 4 times 3 times 2 times 1. So decrease all the way down. So that one is 24. 5 factorial, 5 times 4 times 3 times 2 times 1. Keep going till you end at 1, which is 120. So your calculator should have one of these buttons. Depending on the type you have, it might be under something called probability, like it says PRB on it, but you should see like an exclamation point on there. The other thing that's kind of unique is if you look here, you have 3 times 2 times 1. That's exactly 3 factorial. So what you can actually do is 4 factorial is 4 times 3 times 2 times 1. You can pick off that top number and get the next number factorial. Same thing down here. Change the color. You have 4 times 3 times 2 times 1. So 5 factorial, you can pick off the 5 and get 4 factorial. And then likewise, you can also pick off the 4 and get 3 factorial. You can pick off the 3 and get 2 factorial. So that's one of the really great things about factorials. Okay. The other thing we have to define is 0 factorial. So this one's going to be a little bit strange. This is equal to 1. Okay. So thinking about this in terms of arrangements, there are 6 ways or 3 factorial ways to arrange 3 objects. 0 factorial will be the number of ways to arrange no objects. There's one way to do that, you don't. So 0 factorial is equal to 1, since there is one way to arrange 0 objects. Okay, so it fits in with our pattern, right? So now that we've got this, let's try a few examples. And we're going to come up with another permutation formula, or maybe you're not going to use everything. Okay. So maybe 7 pictures are to be hung on a wall. Okay. We want to figure out how many ways can they be arranged from left to right. Okay. So here that order matters. If I have a picture of a dog and a cat, the way I put it on the wall makes a difference. So this is going to play a role in that next section. So here, the order of the picture matters. Okay. And this is where we just use factorial. There are 7 factorial ways to arrange the picture. Okay. And so let me see if my calculator is that under here. Where's my calculator? I know I have one on here. Just scroll, there we go. Okay. Clear all of this. I don't want an add. I don't know if this calculate. Oh yeah, we do. So we do have a button that is for factorials. So if I want to do 7 factorial, I'll do 7. I have to shift it to get my factorial. So if I want to arrange 7 objects, I have 5,040 ways to do it. If you want to do it by hand, you can. 7 times 6 times 5 times 4 times 3 times 2 times 1. There are 5,040 ways to arrange 7 objects. So this is equal to 5,040. So there are 5,040 ways to arrange the pictures. So a lot of ways that you definitely don't want to sit there and go through and try to figure out. You would not be able to. Okay. Now our last main formula that we have is going to deal with maybe I don't need everyone or everything from my collection. I'm only going to pick a certain number of them and put them in order. So let's try an example to see if we can figure it out, kind of going through this method, and that's going to lead to a formula. Okay. Maybe there are 9 people in a club. So there are 9 people in the math club. Got to make it specific to us. Okay. Collectively, you decide to put each person's name in a hat and randomly select a president, a vice president, and a secretary. How many different outcomes are possible? Okay. So now I'm not using all 9 of my people. I'm going to put the names in a hat. First person I pick out is president. Next person I pick out is vice president. And then the last person I pick out is secretary. So the order they come out of the hat does matter. So kind of drawing our picture, I have 3 positions. I've got my president, my vice president, and my secretary. Okay. Starting out, I have 9 people that I can pick to be president. 1 person gets selected, so you can't be president and vice president. So there are 8 people remaining in the hat. I've now picked my vice president. I have 7 people remaining for secretary. okay? And so if we multiply these, that's 9 times 8 times 7, which is 504 possible outcomes. So you have a lot of possibilities. Okay. But now if I change this and there's 1,000 people of the club and 50 of them are going to be selected for positions, you don't want to do this by hand. So this isn't going to be the most easiest method always. So what I'm going to do is I'm going to relate this to factorials. We ended up with just 9 times 8 times 7. Okay. Really, if I was arranging those 9 people, it would be 9 factorial. So all we're left with is 9 times 8 times 7. I'm going to add in all of the remaining stuff to get 9 factorial. So multiply 6, 5, 4, 3, 2, 1. But if I do that in the numerator, I've got to do it in the denominator. So this way those two cancel out and land you back here. So essentially I'm reverse engineering this formula. Okay? Because what happens is in the numerator, I have 9 factorial. In the denominator, 6 times 5 times 4 times 3 times 2 times 1 is 6 factorial. And if you noticed, we had 9 people. From them, we chose 3. Well, 6 is 9 minus 3. So in the numerator, this represents the 9 people. From those 9 people, we chose 3. And that order matters. When the order doesn't, that'll be the next formula from section 11.8. So this tells us the number of permutations possible when R objects are selected from N objects is NPR. So from not N, we're permuting R objects. So the formula we have is you have N factorial divided by N minus R factorial. So the way you can think of this, from N objects, we're arranging R. If the order doesn't matter, then that's going to be our combination from the next chapter. Okay. So let's just do one more example, and that will be the end of this video, and then we'll pick it up in the next video. We're told a teacher has 10 students. And she will select 4 to win a prize. If each prize is different, so the child that gets selected for each one is going to make a difference. In how many ways can the prizes be awarded? Okay. So this one isn't so bad that you can do it with our lines. You've got prizes, so prize 1, prize 2, prize 3, prize 4. For that first kid, or for the first prize, she has 10 people to choose from. Now that person's been selected, so she has 9. That person's selected, so she has 8, and then 7 for that final prize. So we just multiply these together to get 5,040 ways. But in terms of permutations, the order she selects the kids is important because they will get a different prize for a different order. So from 10 kids, she's going to permute 4. Okay. So using our lovely formula we have up here, this is equal to 10 factorial divided by the difference of those two, 10 minus 4 factorial. So it's 10 factorial divided by 6 factorial. And you can just plug this into a calculator at this point, really. You have a button for exactly this on any handheld calculator, but you can simplify this by hand. You pick off the 10, pick off the 9, pick off the 8, pick off the 7, and then you're left with 6 factorial. And same thing here, it makes those cancel. And you get 10 times 9 times 8 times 7, which is 5,040 ways. So still end up with exactly the same thing regardless of the method you pick. This is great, but again, if I tell you you have 1,000 students and 15 prizes, doing that by hand is a lot more complicated. And this method will be really good. So I don't think this calculator has that, but I don't think so, no. Yeah, your phone calculator won't have one. But if you do go onto an online software, let's see. So if you go on, let me go back. If you search Desmos Scientific Calculator, this one's really good for when you're kind of going through your homework. You can type in this, no problem. But the functions that you're going to use are this NPR. You'll need this for the next section. But ultimately what you do is from 10 objects, you're permuting 4. So you have 5,040 ways to go about selecting the kids for these prizes. Okay. So this is what your button should look like on any calculator that you're using. It's going to have that same kind of look to it. You might just have to search to be able to actually find it. So what we went through last time is if I had a certain amount of objects and I wanted to order them, say I had 15 objects and I wanted to order 3 of them, we figured out this method of permutation to actually count through all of those possible ways to arrange those objects. So we kind of learned a shorthand for when the problem's simple enough to input how many choices I have in each of these positions. So if I have 15 objects and I'm choosing 3, I've got 15 in the first spot, 14 for the second, and 13 to choose from, and I just multiply them. So this would be 15 times 14 times 13, or again, it ended up simplifying to 15 factorial over 15 minus 3 factorial. So from 15 objects, we're permuting 3 of them. Okay. So when you have, 100 objects and I'm going to order 70 of them, I don't have to sit here and actually calculate this by hand. I do have a nice button on our calculators that are going to go ahead and calculate this for us, or we can use factorials to our advantage and do that by hand. So really, we just have one last little topic now about when there's repetitions. So let's look at a second example now that we have this formula. So how many distinct ways can we permute the letters which is B, O, B, where each of these B's are distinguishable by color. So basically we can tell those different B's apart. So the green bee versus the purple bee creates a different order. Okay. So we have the current order that it's in, BOB. I can keep the green bee first and switch the B and the O. I can now put the O first and then the green bee and the purple bee. I can put the O first and then the purple bee and green bee. So those are 2 different orderings because I can tell those colors apart. And then finally, I can put the purple bee first, and then I have 2 options for those second letters, okay? So kind of pairing these off, these both spell Bob, but they're a different order. These both spell BBO, but they're different to each other. And these are both Bob, but they're different from each other because I can tell the B's apart. So these pairs are different because the letters are distinct. Or distinguishable. So I can tell them apart. So there are 3 factorial, which is 3 times 2 times 1, or 6 ways. Okay. Or from 3 objects, I'm going to arrange 3 of them. So you could do 3, P, 3 as well. And you should get 6. Okay. But now if I change this, and I can't tell the difference between these 2 B's, I run into a different scenario because now these look exactly the same, and I only really have 3 options now. So how many distinct ways can we permute the letters BOB, where the B's are not distinguishable? Okay. And so basically from this ordering, I've got the word Bob itself, I've got BBO and OBB. So I end up cutting the second pairing down. So there are 3 ways. Okay. So what happens now if I've got a lot larger amount of numbers, or a lot larger amount of letters, and I want to arrange those, but I have repetitions? How could I possibly do that? So we have another formula or another method to kind of tell us that. So the number of distinct permutations of n objects where n1 of the objects are identical and 2 of the objects are identical and then you keep going. I have a bunch of different groupings of identical objects. So NR of the objects are identical. Is as follows. Okay. If I just arrange those n objects, you have n factorial ways to do it. So in that first example, I had 3 objects, 3 factorial ways. But I need to take out these repetitions. So what I do is multiply by the number it repeats. So one object repeats n1 times, I'll divide by n1 factorial. A different object repeats n2 times, divide by n2 factorial. And you keep going through this, you divide out by the number of those repetitions factorial. So like this last example, I had 3 objects, and this object repeated twice. So in the prior example, we arranged 3 objects where 2 or the B's repeated twice. So we have 3 factorial, 1 object repeated 2 times, so I divide by 2 factorial. So again, if you calculate that or plug it in your calculator, that's going to be exactly 3 ways to permute them. Okay. So you want to count based on this grouping. This particular thing has this many repetitions. This other object has this many repetitions. You just divide out by that number of factorial. So let's try another example, and this will be our last example in this section. We want to determine the number of permutations of the letters of the word statistics. Okay. And so these S's are not able to be identified one from the other. If I swap these two S's, it gives me exactly the same thing. So I have a bunch of different repetitions that end up happening. So in total, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 letters. Okay. So there are 10 letters. Of which we have 1, 2, 3 S's. So 3 of this one object. We've got 3 T's as well. So these repeat. And then we also have 2 I's. Okay. So if I were to actually be able to distinguish, I've got 10 objects, I'm arranging all of them, I have 10 factorial ways to do that. So in total, there are 10 factorial ways to arrange these 10 letters. But since 3 are S's, I've got to divide out by 3 factorial. 3 are T's, so I divide by another 3 factorial. 2 are I's, so we divide by a 2 factorial. If I had another letter that repeated 3 times, divide out by another 3 factorial. Okay. So again, you can plug this into a calculator. If you want to do this by hand, you can pull out the 10 and get 9 factorial. Keep pulling off numbers until you land at 3 factorial. So this way, some of those 3 factorials cancel. So 3 factorial over 3 factorial disappears. And we're left with 10 times 9 times 8 times 7 times 6 times 5 times 4. 3 factorial on the bottom is 3 times 2 times 1. 2 factorial is 2 times 1. So we get some simplification. 3 times 2 is 6, so those cancel. 2 over 4 cancels and leaves you with a 2 up top. So we're really left with nothing in the bottom. We're just left with this in the numerator. So in total, there would be 50,400 distinct ways to arrange the letters of statistics. Okay. So that is it for section 11.7.